Okay, so now we are on question 2. It says consider the organic compounds A to F. And then if you've been watching the videos, you are already accustomed at this point with the method that we use in order to answer these questions here. So the first thing that we do is we try to identify the homologous series to which each of these organic compounds belong. So this belongs in the alkene homologous series because of the suffix here in, and then this here because of the OH, it belongs in the alcohol homologous series. And then we have 2,3-dimethyl pentanoic acid, which should be a carboxylic acid. And then this one here, because of the triple bond, we know that it should be an alkyne, so it belongs in the alkyne homologous series. And then E here, because of the double bond oxygen on the first carbon, we know that this should be an aldehyde, right? And then this F, because of the Br halogen there, there should be a haloalkane, right? Then let's now check how we answer those questions. So now that we have identified everything, it should be easier for us to answer this. Now 2.1.1 says, write down the letter of the compound that is an alkyne. And then as we can see there, that's D. Then 2.1.2, write down a letter of the compound that is a haloalkane, as we can see it there, F. Now, 2.1.3 says, write down the letter of the compound that is the general formula, CnH2n plus 2O. Now, note that this here is not an alkane, obviously. And then from the options that you are given here, there is no alkane. But then, this one here, you need to be very careful of one thing. When they give you the general formula of alcohol in your textbooks, normally you see it like this, CnH2n plus 1 and then OH. But then this here can also be the general formula of an alcohol. If you take this hydrogen here from the hydroxyl group and you count it amongst the other hydrogens here, then this becomes 2n plus 2 and then O, right? So this is the loophole that they created, because most of the textbooks, you normally see it like this, but then when they give it to you in an exam paper, it is usually in this format. So also they can do this in terms of your molecular formulas. So in your textbook, you might be used to something like C4H9 and then OH. And that's how you are able to see that this is an alcohol. But then it gets confusing if you get C4, H10, and then O. A lot of you are quick to say this is an aldehyde or a ketone. But then note that if this was an aldehyde or ketone, it would be C4, H8, and then O. And then why? Because the general formula of an aldehyde or a ketone is CnH2nO. So with the aldehyde or ketone, the number of carbons here are exact, the number of hydrogens are exactly double the number of carbon atoms. But then with this one, you can see that the number of hydrogen atoms are double the number of the carbon atoms plus 2, right? So that's the difference here. With an aldehyde or ketone, you have this, but then with an alcohol, you can have that CnH2n plus 2 and then an oxygen. So this is something that you really, really need to check when it comes to your exams, right? So note right now that CnH2n plus 2O is the general formula of an alcohol. So that means our correct answer here has to be B. Now 2.2 says, is compound A saturated or unsaturated? Now obviously we'd have to understand the difference between saturated and unsaturated. Now, saturated means that there are single bonds between the carbon atoms, and unsaturated means that there are multiple bonds, so double bonds or triple bonds between the carbon atoms. Now, let's look at A. A is an alkene, so obviously we know that alkenes are characterized by double bonds between the carbon atom there. So obviously A has to be unsaturated. So the only saturated hydrocarbon are your alkanes, right? So give a reason. So we said unsaturated, and the reason for that is because there are multiple bonds between its carbon atoms. Right, so there are multiple bonds between the carbon atoms of compound A. Let's say between the carbon atoms of the compound. Okay, nice. Then 2.3 says write down the structural formula of compound C. Okay, so to write down the structural formula of compound C, obviously we have to start with our longest chain. And as we can see here, pent means we have to have 5 carbon atoms on our longest chain. So 1, 2, 3, 4, 5. Now we know that the functional group of the carboxylic acid is always attached to the first carbon. So let's indicate that on the first carbon. So we know that it is a double bond oxygen and then also OH. So this is what we know as the carboxyl group. The name of the functional group is carboxyl group. And then now let's indicate our substituents. We have our methyl branches at carbon number 2 and 3. So carbon number 2, there is a methyl branch. Then also in carbon number 3, there is another methyl branch. And then at this point, you only need to fill in your hydrogen atoms. Hydrogen there, hydrogen, hydrogen. And then there we go. Obviously, here we cannot fill in a hydrogen because 1, 2, 3, 4. There are already 4 bonds around carbon, and that's the maximum that it can have. Okay, so that's it. Our 2,3-dimethyl pentanoic acid looks exactly like that. So obviously, we chose 2 number from this side. And then, okay, we have IUPAC name of compound D, right? So where is compound D? Note with compound D there that we do not have a branch. A lot of you, when you see this, you think this is an ethyl branch, but then you can't have a branch at the corner there. So once we have a hydrogen closing off here, then this carbon is at the corner, therefore it bends and goes like that. So there should be one long straight chain here. This is one long straight chain. Also, this one is at the corner, so it extends to one long straight chain. So meaning now we have to check how many carbons are on this long chain. That's 1, 2, 3, 4, 5, 6, 7. So that's halved. But then again, we must choose to number from the side where we see the closest disturbance. If we number from this side, we can see 1, 2, 3. Our triple bond is occurring in carbon number 3. But then, however, if we number from this side, this is 1, 2, 3, 4. It's occurring in carbon number 4. So obviously, we must number from the side that has the earliest disturbance. Therefore, we'll choose to number from this side up here. 1, 2, 3, 4, 5, 6, 7. Then to come up with the name 2.3.2, that's hept for 7. And then dash indicate the position of the triple bond. So hept 3. And then give the suffix coming from the homologous series of which this compound belongs. So that's hept 3-wine. Now 2.4 is asking, is compound B a primary, secondary, or tertiary alcohol? Give a reason for your answer. Now this is B here. If you want to get a correct answer for that one, the advice is it is better to draw that as a structural formula so that you get to see what is really going on. Right, so you will have your carbon here, and then this CH3 indicates that this has to be a methyl branch, but then we have a 3 here, so meaning that we have to repeat this methyl branch 3 times. Right, so how can we do that? Obviously, if we can have this, so that will be a methyl branch over there. And then this here, another methyl branch. And then also here, a methyl. So that's the meaning of the CH3 and a 3 there. And then we have to have this bonded to an OH. Right. So looking at this here, however you choose to number this, you will note that if you say this is 1, 2, 3, so this would be your longest chain, or 1, 2, 3, right? So let's say maybe you go like this, 1, 2, 3. That would be it. So in other words, that is 2. So that's 2 methyl 2 methyl propan dash 2 all, right? But then remember, we should give the IUPAC name. We must indicate whether this is primary, secondary, or tertiary alcohol. So, okay, to come to that, let's look at the carbon that is bonded to the OH here. So this is the carbon bonded to the hydroxyl group, but then how many other carbons is it bonded to? It is bonded to that carbon, this carbon, and also that carbon. So that means we are going to say this is what? A tertiary alcohol. And then why is it tertiary? The reason is because the carbon bonded to the OH group, or you can say the hydroxyl group, is bonded to 3 other carbon atoms. So there you go. The carbon bonded to the OH group, the hydroxyl group, is bonded to 3 other carbon atoms. Right. Now, 2.5 says write down the IUPAC name of a chain isomer of compound B. Now, before we can do that, let's understand what is a chain isomer. A chain isomer, it's an organic compound that has the same molecular formula, but different type of chain, right? So if we have this here, the molecular formula is 1, 2, 3, 4. So we have 4 carbon atoms. And then how many hydrogens? 3, 6, 9, plus this one, that's 10. So H10 and then O. So the compound that we should have should also have the same molecular formula. But then it should be a straight chain because already here we have a branched chain, right? So to contrast the branched chain, we need a straight chain. So, okay, if we were to draw a chain isomer, this would be our chain isomer here. So we must have 4 carbon atoms. And then we have our OH here, bonded like that. So not here. Remember, it's in carbon number 2. Sorry for that. So the OH was in carbon number 2, so we need to put it in carbon number 2. Yes, correct. Then remember, it's not positional isomer, it's only a chain isomer. So we must not change the position of the hydroxyl group. So in here, we can then indicate our hydrogen atoms. Hydrogen atoms. And there we go, right. So we haven't changed the position of the OH there. So, but then we are not interested in the structural formula. They said they want the IUPAC name. The IUPAC name of this chain isomer now. So I was just trying to show you how it would look like. And then now let's come up with the name. Let's come up with the name for this. What is the name of that? So this should be butan-2 all. Right. So as we can see, you still maintain the same position of the hydroxyl group. Then we have 2.6. It says compound E has a functional isomer. What are functional isomers? What are functional isomers? Let's check. So by definition, we say functional isomer. Functional isomers are organic compounds with the same molecular formula but different functional groups. So remember, every time we speak of functional isomers, I said remember cake, right? Where we have to note that the functional isomer to a carboxylic acid is an ester, and the functional isomer to an aldehyde is a ketone, right? So remember cake. Now, 2.6.2 says write down the condensed structural formula of the functional isomer of compound E. Note that they don't want you to write the condensed structural formula for compound E. They want you to write a condensed structural formula for the functional isomer. So what is the functional isomer of an aldehyde? E is an aldehyde. We know the functional isomer of an aldehyde is a ketone. So first, let's indicate the structural formula. Before we can come with the condensed formula, I said always try to draw the structural formula and then condense it from there. Now, obviously, we know in order to make this a ketone, all we have to do is move this double bond oxygen to the carbon in the middle of other carbons, right? So that's how we create the carbonyl group. So we can't have it there. So there we go. And then this is supposed to be. So in terms of the condensed structural formula, then this is what you do with the condensed structural formula. This first carbon here, how many hydrogens is it bonded to? 3. So that becomes CH3. This carbon here, it's bonded to an oxygen, and then that carbon here is bonded to 3 other hydrogen atoms. So this is what they mean when they say condensed structural formula. Right. Now, others can choose to show it like this, CH3, then dash, then indicate the double bond oxygen, and then you have CH3. So also this way can be another way of writing your condensed structural formula. Either way, you should be correct. Okay, so that's how you were supposed to tackle all this question for a total of 17 marks.